This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right, welcome again. We'll soldier on some more of the fundamentals and get to our first thermodynamic tool today. So remember the last two lectures, we've built up the basic principles already. We've identified what we are and what we aren't doing. So that was the job of the system boundary, what's inside, what's outside. Inside is what's being analysed, but we treat it inside as a black box. We don't look at the details of the machinery or the equipment, but that is the thing that we're analysing the change of. Outside, we can ignore, except in that if any heat or mass crosses across the system boundary, and in the system boundary we know where it is, it defines the volume, the mass, the shape of what we're working with. And then we went on to establish what are these, what's the working fluid and how do we define its properties. If we're going to be analysing the change in something, we need to know what that something is, and we need to know what are the units or what are the variables that we're talking about when we talk about the change. Shortly after that, we then started to just introduce the idea that there are processes. To change from something to something else, something had to happen. And so today we're going to have a look at some of these processes. Before we do, there was one little bit of hand waving we did, which is to say that everything we deal with is in equilibrium, and it seems like a strange thing for me to be saying when we're talking about change. So we're going to start today by having a look at thermodynamic equilibrium and what it means for this subject, how we use it, and when we can ignore it. And it really is, at the introductory level, it really is a statement to say this thing exists and don't worry about it. So for the next 6 weeks, to acknowledge in my learning, I understand that what we're doing is at thermodynamic equilibrium, and I'm not going to be pushed outside that box in this subject. In future subjects, in future analyses, you need to be aware that the idea exists so that when the rules get broken, you can apply a different tool set. Once we've had a look through, that, we'll have a look at the different most common processes that we'll analyse, and then we'll play around a little bit with the rules that define a perfect gas, and we'll do that because we have two major working fluid sets that we use in thermodynamics. Almost all of our problems are split into two worlds. One is one where we're dealing where the working fluid is what we refer to as a perfect gas, and the other is where the working fluid is not a perfect gas. Again, it seems like an obvious statement, but where it obeys different rules and where instead of having a nice neat equation of state for determining the properties, we have tables and need to look up the properties. So our classification of our working fluid sits in those two baskets. So we'll go through all of that today. Okay. Is there anything that didn't make any sense from the last two lectures? Oh, wow.
Not that much.
Phew.
But equilibrium, does it mean the same concept?
I hope so. I hope so. Let's find out. So we have thermodynamic equilibrium and local thermodynamic equilibrium. So we'll give definitions to these. So first, we're going to walk through. Billiard tables and pool tables get used a lot in this subject because a lot of the subject has to do with bouncing molecules. And so if we imagine a pool table with billiard balls on it, and then we disappear the friction so that they can bounce all over the place and not ever slow down. Imagine that I smashed the balls. So if you've never played pool, you won't have any idea what I'm talking about. I'm going to assume that you've seen a pool table and at least have seen the idea that you begin the game by hitting one ball, imparting a fair amount of energy to it, and then it hits the other balls and they all start to bounce around. Imagine I do that and there's no friction. What's going to happen? Oh, this is important. They won't stop. So what will they do? Oh, well, fair enough. Fair corollary. If they don't stop, they'll keep moving. In the beginning, they're not moving, and in the beginning, only one ball is moving. I've hit one ball. And so how do the other balls start moving? These are not trick questions. I don't want to spend too long on them, yeah?
Transfer of energy.
Right. They all start to bounce into each other and transfer energy. So in the beginning, the energy is not uniformly distributed on the pool table. In the beginning, only one of the balls is carrying energy. The rest have, well, the potential energy, fair enough. They have no kinetic energy. The first ball hits the next ball, a little transfer of energy. The next ball hits the next ball, a little transfer of energy. In the steady state, they're all moving. They don't keep stopping because I don't have friction on this table. In the steady state, they've all bounced against each other on the walls a fair bit. And if there's no friction, what's happened to the energy in the balls? Yeah, and does any particular ball, are we expecting any particular ball to have more or less energy? Right. So if I let them keep bouncing and then I fast forward into infinity, eventually all that energy will be distributed in that pool table and all the balls will be carrying the same amount of kinetic energy. Which seems weird. When you first smash the pool table, you know some of them are going slow and some are going fast. Eventually, we're talking about eventually, they bounce into each other enough and distribute all the energy. So they're probably all moving a little bit slowly, but some of them are hitting the walls and some are not. That exercise of redistribution of energy so that everything in my system is containing the same average energy. This is an analogy for going towards thermodynamic equilibrium. If I were to tell you the energy state of that table, it is difficult for me to tell you that until all the balls are bouncing with the same energy. It's difficult for me to describe the state of that table until all the energy is distributed. So we try to set ourselves, when we say the state of this air is defined by one atmosphere in a certain temperature, and therefore, as we remember, I've given you two variables. I should know all the rest, the viscosity, the electrical conductivity. I should have been able to define that. To be able to say that, all of the air in the room needs to be at thermodynamic equilibrium, needs to be have no ongoing changes in its state. If I don't have that, I can't just make a statement around the air in the room. So, one of the other reasons why bouncing billiard balls or bouncing pool tables gets used is this is effectively gas molecules in a container. The energy of the balls bouncing around is effectively what we are defining when we talk about temperature. When we're talking about the thermal energy of something, we're giving an indication of to how much kinetic energy the individual atoms, the individual molecules have. And they're all vibrating, and the more they're vibrating, the more they're bouncing around, the higher the temperature of the object. They bounce into the walls of the pool table. That average rate of collision with the boundaries is a definition, is an idea for how pressure works. So the pool table walls are receiving an average amount of bouncing, and they're giving it back because we're not losing any energy out of the system. But that is what gives rise to pressure. So if I have a box or a balloon or this lecture theatre and all the molecules of air are bouncing off each other and the walls, the pressure in here is the bouncing of those molecules on a system boundary. The temperature in here is how fast those molecules are vibrating. So one of the reasons why you see pool tables turn up a lot in introductory thermodynamics. Plus, I think there was a lot of engineers spending time on pool tables. So, once I've hit that state of equilibrium, then I can define the properties of that working fluid. That's important, because the opposite is true. If I'm not at thermodynamic equilibrium, I can't, and then I can't begin my thermodynamic analysis. So we have a problem. But we'll begin by how do we know that something's in equilibrium. So, if everything's the same temperature, if everything's the same pressure, then this is generally thermal equilibrium. The main thing about thermal equilibrium is that something is the same temperature as something else. So it's one of the advantages. And when I waved my hand on day one that there was a zeroth law of thermodynamics, which is if something's at the same temperature as something else, then it's at the same temperature as something else. That doesn't sound terribly mathematically rigorous or useful, but if that wasn't the case, the point of it is if something is in thermal equilibrium with another matter, they have the same temperature. If I didn't have that basic physics principle, basic thermodynamics principle, I couldn't tell you the temperature of something because I couldn't stick a thermometer into something and say that what I'm reading on this device is the same temperature as what I just stuck it into. If the idea that two things that are at thermal equilibrium have the same temperature didn't exist, I couldn't tell you the temperature of anything, which is tricky, unless I sat down and did the statistical analysis of all the molecules that are vibrating and I had some way to assess their energy. So we have this thermal equilibrium. If the temperature is the same throughout the entire system, there are other forms of equilibrium. Mechanical equilibrium, there's phase equilibrium, there's chemical equilibrium. All of them come down to the same thing, which is that if I leave this system forever, nothing will change in that set of properties. So, thermal equilibrium, if I leave it forever, nothing will change in the temperature. Mechanical, there's no change in pressure. So mechanical and thermal we assume a lot. Phase and chemical equilibrium. Phase equilibrium, because we deal with gases and liquids and sometimes solids, this one's important to us, which is to say that if there's no change in the mass of the phases, of the different phases with time, then it is at phase equilibrium. So I've got a lump of water, a lump of water, nice. I've got a lump of ice in a glass of water, and that ice is melting. That system is not at phase equilibrium. If that system were at 0 degrees, it would find a phase equilibrium where I always have some ice and I always have some water, and it wouldn't change that quantity over time. Chemical equilibrium is that if I do nothing, I won't change the chemistry of what I'm doing. It goes deeper than that. It's about the chemical energy contained in the bonds of the molecules. So I'm expecting if something's at chemical equilibrium, it won't catch fire by itself. It won't decompose. It won't rust. Or if it wanted to rust, it's already rusted as much as it possibly can. It won't oxidize. It won't change chemical state. It won't change its chemical energy, which is the key. So we have all these different ideas of equilibrium, and for every single one, we know that most of the time when we're dealing with engineering problems, they're not at equilibrium because we're dealing with engineering problems, which is about dealing with change. Okay, I'm going to skip. This is more of the same conversation. In fact, I've already said almost all of it. Yep, I have said all of it. Good. I do that a lot because I know my notes fairly well. I tend to talk ahead and then put up the text so you can read and say, that is what we were supposed to learn. So, if the stuff we are going to analyze has a habit of changing, and in fact would be boring to analyze if it wasn't changing, how do we deal with this issue of I can't tell you what the state is if I don't know that a system's at equilibrium? And the answer is we get very pedantic and very petty and very small-minded about what our definition of equilibrium is. We come up with an idea called local thermodynamic equilibrium, which is to say, at the moment that I ask you, what's the state? You can go, it was 7 degrees, it was 1 kilopascal, it was whatever. Right then. What's the state now? It's different. Okay, it's changed. Is that at a different thermal equilibrium? When I asked you and when you gave me the answer, if the system was at local thermal equilibrium in that moment, I can get around this. So we need to have an idea about how fast can I ask that question? How fast can you measure? How fast can you tell me the answer before we break the rules? And that's the rules of local thermal equilibrium. If I can get away with it, if I can pull it off for most of the problems we analyse, we're okay. No spoilers. The answer is yes, we can. We need to be in a situation where the properties are changing slower than the rate of collision between molecules at that point of space. So that's our metric. Our metric is how fast the molecules bounce into each other, which luckily for us is really, really, really quick, of order e to the minus 12 seconds. Most of the time, if I measure the temperature of something, I've been measuring for a little bit longer than that. And so at the point where I read you the temperature, the system was at local thermal equilibrium. The thing that I measured was at local thermal equilibrium. If I draw my boundary system bigger and cover the whole universe, maybe that wasn't the case. But for the system I've drawn, when we do these analysis, in fact, basically for the rest of this semester, that will be the case. Now, this can break. This can break when I'm dealing with systems where molecules don't touch each other of order e to the minus 12 seconds, 2e to the minus 12 seconds. That happens in space, where the molecules are so far apart that they can't redistribute their energy fast. Even though they're small and they can bounce on each other, there's no one to bounce off. And so you can have local temperatures in space that are crazy high because they haven't had a chance to bounce into someone cold yet. It also happens in plasma physics, and it also happens, it can happen in nuclear reactions, things that happen fast or where the molecules are far apart. There are times when local thermodynamic equilibrium breaks down. We don't do that for the next 6 weeks. And that's, the moment I said that about 5 minutes ago, most people stopped listening. Okay, tick, got it. But one day you may go to a stage where you do need to deal with it. All right, so we've patted ourselves on the head and we've said that's okay. I can tell you the state of things. I can tell you the properties in something. The other thing that we left open on Wednesday was any kind of definition around processes. Now, often with changes, I don't need to tell you what the processes were. If I can tell you the state of 1 and the state of 2, you can tell me the change in energy between 1 and 2. Doesn't matter how I got there. But there are a lot of problems, particularly around the efficiency of getting there, which is a really big deal for engineers. The efficiency of getting to the end game, where I do need to know what the process was. And there are times where the amount of energy used to get there, well, there's the same thing, said in a different way. The amount of energy used to get there or the amount of heat transfer to get there is different depending on how I got there. So we need a toolbox, a mathematical toolbox of processes that make our life easy, and then we hope that we can describe all of our problems with that toolbox. Which means I'm going to introduce our most used graphical tool for this field, which are the property diagrams. And a property diagram is a 2D graph with two properties on the axes, and I draw a dot on it somewhere, and that's the state that I'm at. So it's not hard. If the properties I draw are pressure and volume, and I tell you what the pressure is, and I tell you what the volume is, two independent variables, actually I'll do specific volume to make sure I stay true to the thermo, specific volume, which gets a little, so this was V, that's volume. This is important. Nu is what we use for specific volume, which is volume per mass. Okay? I do that so that if I mark a point on that graph, I've given you two independent intensive variables, which means I have actually defined the state of my working fluid. If I draw another point on the graph, this is state 1, and this is state 2. Could that actually show up? I think that's really bright. Okay, that's good, it's working. This is state 2. I've got two x's, two states. If I said it was the same system, if I said these two states were the state of the same system inside the same system boundary, something happened to get me from point 1 to point 2, some process, and it could have been anything. Could have been in a straight line, could have been a corner, could have been a wobble, could have been a curve. Each of them has a different maths behind it. Each of those curves is represented by a different mathematics. Each of them represents a different physical process. If my two processes were straight up and straight across, the first process was constant volume, and the second process was constant, right, constant pressure. So there's a couple of processes, basically straight lines on these property diagrams, The straight lines on the property diagrams are actually super useful because it allows me to quickly do the math. So maybe I didn't know from here to here, but maybe I could say if I had a constant volume and a constant pressure approximation, I could do the maths of this quite quickly. So we're going to do that kind of decomposition quite a bit in this subject. The other thing to point out about this is these guys could be anything. I could also write down, imagine we've learned entropy. I could write temperature and entropy. Entropy, the symbol is S. That's, again, a spoiler, but we'll get there. I could put any combination. I could put enthalpy, internal energy, any of our properties, and we'll get familiar with each of the properties over the course of the next few weeks. Provided the two axes are independent, drawing a dot on the axis is to find the state of the problem. Drawing two dots gives me initial and final conditions. I can analyze the change in energy. Given two dots and a line, I can then talk about the process to get from 1 to 2. So we use these maps all the time. Our two favorites are the ones that I've drawn down, which are pressure versus volume and temperature versus entropy. We'll do them a lot. And we will learn the code words for each of these processes. And now the code words nicely almost all begin with ISO something, or ice something. And ISO means constant. And so we have isochoric, isobaric, isothermal, isenthalpic, isentropic, and then adiabatic, which doesn't have ISO, but it means constant something or other. Actually, it doesn't mean constant. It means no heat transfer. Each of them gets a different maths. Each of them gets a different line. The lines are different depending on what type of diagram you put them on. So a constant pressure graph doesn't look like a straight line if pressure is not one of my axes. That might sound obvious. But you have to learn, you have to be able to map to different property diagrams so that you can analyze different aspects of the change. Because we tried to set ourselves the rule that everything was okay when I was at local thermal equilibrium, and local thermal equilibrium is a pretty small scale, unfortunately on that scribble, I have to pretend that what I'm actually drawing is a set of infinitesimal dots. It's effectively integral calculus, that each infinitesimal step along the line was done at local thermal equilibrium so that I can move from one state to the other and that the points on the graph actually represent thermodynamic states. If I didn't impose that rule, the line would have no meaning. If it wasn't at local thermal equilibrium each infinitesimal step along the line itself, the points on that line would have no meaning, even if at the end I'm at thermal equilibrium. So there is maths behind what we're doing. And there's textbooks and textbooks of maths behind what we're doing that we are short-circuiting just to let us be able to use the tools. With all the ISO things, there are some terms that are, should be obvious. For example, isothermal, you should be able to guess. There's a constant temperature. There are other things that there are words, Latin words, that you don't come across every day or ever. One of them is isochoric, and I don't know anyone who's ever used the word choric outside of thermodynamics, and so this is just one of those things where you've got to learn it. So a constant volume process is also called an isochoric process, and this is part of my job while I'm in class. Isobaric, some people have heard of, some people haven't, depending on what path you've walked to get here. But they're isobaric. If you keep in your mind that we're measuring atmosphere pressure in terms of bar. So isobaric is constant pressure. And then enthalpy and entropy. Enthalpy is a form of energy, entropy is a form of disorder. You can have isenthalpic and isentropic processes. All of these are straight lines provided that it's on provided that that property is on the axis. When the property is not on the axis, you need to know the maths of how that property connects with others. So I say that because if I had a constant temperature process, but I was on a pressure volume graph, it wouldn't be a straight line, but I would need some information about how does pressure and temperature change for me to plot a constant pressure. Luckily, we'll do that in about 5 minutes. Okay, the one that jumps up as not having the word ISO in it is this adiabatic. Adiabatic means no heat transfer. If you see more code words, if you see the code word fully insulated means no heat can transfer across the system boundary. Fully insulated means adiabatic. Adiabatic means fully insulated. They go both ways. That's important because when we're analysing energy transfer, we need to keep track of all the different ways that energy can change. One of them is by heat transfer. And if I tell you it's adiabatic, I can cross that term out and it becomes 0. If I tell you there's no change in the system energy, I can cross out the work term. So we were going to learn lots of different tips and tricks about terms that I can cross out and when I can cross them out. And it's connected with the maths of the processes that we're dealing with. Okay, I said on Wednesday one of the reasons why we boil kettles a lot in thermodynamics or intro to thermo is that the water in a kettle is open to the atmosphere, which means that the exercise of boiling water in your kitchen is a constant pressure process. If it's a constant pressure process and I had a PV diagram, you know what, it's going to come up on the screen, so rather than jump to the doc cam, I'll just put it up. If it's a constant pressure process and I have a pressure versus specific volume diagram, I'm going to go straight. But what is it that I'm changing? It's an isobaric process, constant pressure. I pass through a series of local thermal equilibrium along the process path to another point on the property diagram. So it looks like a straight line. How do I know my specific volume is going up or down when I boil the water? So I'm boiling the water, and what's happening to the level of water? It's getting lower and lower and lower. So how can I say that my specific volume is increasing?
Because it's divided by the mass.
Okay. That's one of the key things, is I divide by the mass. There's another important thing, which is when I look at the water level, all I'm looking at is the liquid water. My system, the whole mass of that system, the state of a boiling liquid includes a representation of how much of it is a vapor and how much of it is a liquid, in liquid form. And we will deal with, we will define that property, which is referred to as quality. As I boil the water, I'm turning more and more, per unit mass, I'm turning more and more of the liquid into a vapor. So if I keep track of the mass of my system, as I add energy, I'm turning more and more of it into a vapor, which means that more and more of it wants to occupy a larger space, which means that the specific volume per unit kilo of water that I'm keeping track of, the specific volume is increasing. What I see in the kettle is a level of liquid water reducing because I'm turning it into steam during that boiling process. So constant pressure all the way through the boiling, and on that journey I'm turning liquid water into gas, and if I keep track of all of my mass, the specific volume, which is the the average volume per unit mass of water, is going up and up and up and up and up as I boil the water.
What is average? What? Say
I keep track of all my water. I keep track of all my water. I keep track of the thermodynamic system that I'm analysing. And if I turn some liquid water into gas, if I catch it at an instant time, I don't say just this one bubble of air. If I just analyse like one vapour bubble, its vapour fraction is 100% vapour. If I just analyse a little bit of water, its vapour fraction is 0. If I analyse my system, I have a lot of bubbles and some water, and so the average volume per unit mass of that system goes from small to big. So that's a good question. I like that one.
Like, isn't specific volume reciprocal on density?
It is, which also means my density is going down. So if this were a pressure density graph, my arrow would go the other way. Good. You know what's interesting is over now 4 years of teaching this subject, I've never once been asked a question about this. So, which also means I've never once had people paying attention to the detail of what I'm saying. So thank you. Okay. That amount of hand waving on the processes is basically an introduction, a get to know you. Please, here are your processes. We will use them more and more and more. It's not enough to start mathematically using them apart from the straight lines on graphs. And we will come back and revisit the processes over and over again. A lot of the analyses that will be done are saying from state 1 with process X, what's state 2? Or from state 1 to state 2, what process would give me this amount of energy transfer, or et cetera, et cetera. So understanding the delta between 1 and 2, and also how we got there, is the core of the thermodynamic analyses we will do. So we step on one more round of definitions, and that is the idea of the perfect gas. So on Wednesday, when I waved my hand at the ideal gas law, so perfect and ideal we use interchangeably for when we're talking about perfect gases or ideal gases. When I waved my hand at the ideal gas law and said we'll use this a lot, that was because half of our world splits into analysing perfect or ideal gases as the working fluid, and half of our world splits into using vapours or boiling liquids as our working fluid, specifically water and steam. So today we'll revisit the maths and play around a little bit with some of the rules, because again, as a code word, if I say in a question blah 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 is a perfect gas, it triggers you to be allowed to use this set of maths. And if I say blah 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 is a vapor, it says you can't use this maths, you have to use this maths. So it's one of your jobs to spot the code word and say, okay, I know which tool set I'm getting. The perfect gas or ideal gas tool set was developed or came about through two different scientists having a look at how these things behave. And this is experiment after experiment after experiment after experiment after experiment. You don't get to this level of generality until you've done your homework, which is to say, try the same thing on every gas you can get your hands on and every combination of gas you can get your hands on until you convince yourself this is real. So 1662, not a lot on TV. Guy had a lot of time on his hands. He did this. This is Boyle. And Charles also did this. He viewed it in a different way. So one of them was looking at if I hold the temperature constant, what's the relationship between pressure and volume? And Charles looked at it the other way. He said, if I hold pressure constant, what's the relationship between volume and temperature? Which gives you a hint that the two ideas are somehow connected. But it begins with, if perfect gas, therefore these things. What's interesting about these two laws is, if these things, therefore perfect gas. So if you can show these two rules, you have a perfect gas. If you state that something's a perfect gas, you have these two rules, which is nice. These two experiments look different on a process diagram because one's a constant temperature process and the other a constant pressure process. So on a PV diagram, the constant pressure process is easy. It goes this way. But there's a relationship between volume and temperature. Now, neither volume nor temperature show up on volume shows up on our, I shouldn't have said that. Volume shows up on our PV diagram, but not temperature. If I had a PT diagram, I'd have a different graph. But that's not so much the point there. There is a third law which you sometimes see in some textbooks, and I don't play with it a lot, which is also says that the specific heats of the gas are constant during these processes. We haven't even introduced specific heat yet, and the law itself is called Reynolds' law. This is not, I don't find that one mathematically useful. The first two I find mathematically useful, and we play with them all the time. And the specific heat one I don't find helpful yet at this stage of analysis. Now, the neat thing is, almost everything that's a gas in our normal world is an ideal gas. which lets you make that assumption really quickly. If you're doing a problem, say you're in charge of the problem, you're in charge of the analysis, and you realise first thing, I'm in charge of the system boundary, and I've drawn that, and I'm in charge of what's inside and what's outside. Second thing, I'm in charge of defining the working fluid, and I've done that, and I've said the working fluid is going to be air. So that's going to be the medium that transfers my energy, or changes, the thing that I'm measuring the state of. And then you're in charge of saying, well, am I looking this up, or am I treating it as an ideal gas? And you say, well, how can I verify, how can I allow myself to make that decision? Effectively, if it's a gas in your normal experience, you can treat it as a perfect gas. Now, that rule isn't mathematically fixed. Your normal experience might not be normal. The important thing is how far away from the critical properties you are of that gas. Which is to say, when you are super hot or super compressed, generally you're getting close to breaking the rules. If you're getting close to condensing out of vapor phase, out of gaseous phase into liquid phase, generally you're not an ideal gas. And that's the rule that gets broken with water. And when we're at super high pressure, that's a rule that gets broken with air or nitrogen or argon or any of these gases. But by and large, for our thermodynamic analyses, air, nitrogen, argon, ammonia, these things are, scratch ammonia, that's a vapor problem. These things are perfect gases, or ideal gases. So what? So what? We put them together. Oops. The slide vanished. Oh no, it's okay. We put them together and we try to get from state 1 to state 2. Now, if I don't know the process between state 1 and state 2, I can't tell you much about state 2. Can't tell you much about how I expect it to behave. So, why would I have this exercise? My purpose of the exercise we're about to do, is to show that I can connect Boyle's law and Charles' law, which is to say there is a relationship for a real gas, for a perfect or ideal gas, there is a fixed relationship between pressure, volume and temperature all at the same time. We kind of already know that because we've kind of already got the ideal gas law, but we just haven't proven it yet, and so this next few minutes is just the exercise of proving it. So that's the diagram, and I'm going to do this one on paper because it's easier to follow on paper. I've got nice little reveals on this, and it doesn't actually help understanding what we're doing. All right. So we get that graph back up on page. I had point 1 here, and point 2 over here. It was a pressure volume graph. And I say to you that it is an ideal gas. You go, okay, that means Boyle's law and Charles' law apply, which means that I can connect for a constant temperature process, I have a PV relationship. For a constant pressure process, I have a TV relationship. So what I want to do to establish a connection between pressure, volume and temperature, what I'm going to do is get two processes. One lets me use Boyle's, one lets me use Charles, and make my way over to state 2. So with Boyle's law, we had PV equals a const. This is small writing. If T const. With Charles's, V on T equals a const. If P const. So I've scribbled that down. It was in your notes. Forgive me if you can't read the writing on that. Which means let's first do a constant pressure, a constant temperature process. And then once we've done that, we're also going to do a constant pressure process. Now, when I'm sketching out two processes and I hope they meet somewhere, you kind of just have to draw some lines around. So I'm going to use this one to get to A. I'm going to make up a point A somewhere. And I'm going to use this one to get from A to 2. So what we do, if PV is a constant, so if the relationship between P and V equals a constant when temperature is constant, what shape of line do I have to use? I've got a straight line, I've got a nicely defined arc, I've got no hand waving at all. Do I have a straight horizontal line? Anyone for a straight up and down line? The hand waving arc, is there a word for that arc? Not something I actually want to test you on. If you know the word, it's hyperbolic. If you don't know the word, that's okay. But a hyperbolic looks like a pleasant curve this sort of way. Never touches this axis, never touches this axis. Okay, so it asymptotes to V and it asymptotes to P. And it goes through 1. And I don't know where A is yet. I just know that it's on that line. That line is my constant temperature process line. Now, you know, there's no numbers on here. So whether I drew a smooth curve like this or not, doesn't really matter how pleasant a curve it is, provided it doesn't cross P and it doesn't cross my axes. I do know that if I'm going to use this guy, I need to do a constant pressure process. And a constant pressure process is a straight line through 2. If I could draw a straight line through 2, that would be good. And so let's say where they meet is A. So now, to get to 2, I'm going to use Boyle's law and then Charles' law. I know that I'm allowed to use Boyle's law and Charles' law to get to 2 because I've said it's an ideal gas. So, using one ideal gas rule I get here, using another ideal gas law I get here. The first one says, so I want to make a point that this location makes no difference, which is just some mathematical crossing stuff out. So we've got pressure 1, specific volume 1. If it's a constant, that means it's the same here as it is here. So, equals P, A, V, A. I've got the temperature here is the same as the temperature here. TA equals T1. That's all good. That's for process 1. Process, whatever. Process big A. And then for process, let's say 1 to A and A to 2, we can do a similar thing. We say TAV2 is equal to T2VA, and the pressure was constant, so PA equals P2. So these guys, by letting the rules exist, I've gone from 1 to there, from A to 2, from 1 to A to 2. This is what I know because of Boyle's law. This is what I know because of Charles' law. If I start to put them together and see if I can get rid of the A's, well, I wouldn't do this if I couldn't, but it's nice to see it happen. I say it's nice to see it happen. I start to substitute things in. So, I want to get rid of A. I can redefine that in terms of this one. So if I get, this gives me TA equals T2VA on V2. I've got an A in here, which I'd like to get rid of. And I can define that in terms of maybe this guy. So here I can say VA equals P1 V1 on PA. So here's another guy. And this guy I can bring up here and say, well, PA is actually P2. So let's start. Now I've got things going all over the place now. If I start putting them down, let's go here. I'll get T1 V2. And how did I get that? I plugged in T1 here. T1 V2 is equal to T2 VA P1 V1 PA, which I keep substituting in. I get rid of my PA, equals to T2. This was easy when I was writing it down because I left myself out of space. What's the best way for me to turn that around? Oh, that doesn't work. There we go. These are super convenient until you have to do something that goes over page. What I end up with here is T1 V2 equals T2 P1 V1 on P2. And then if I shuffle this around, at this point I've got rid of my A. So I've substituted in everywhere I can get rid of A's. I've got a P2 in here. I've made another an expression for VA which I can substitute in. When I've got rid of it all, if I turn this around, I get T1, P1, V1. Put all the ones on one side. T2, P2, V2. Put all the 2's on another side. What this tells me is that temperature, pressure, and volume are connected by a constant. And if you think about the ideal gas law, which is that PV equals MRT, if it's PV, or if I take a specific volume. So let's do the form that most people know, PV equals MRT. If I take this guy over, PV on M equals RT. V on M is specific volume. Volume divided by mass. Oops. V on M is specific volume, volume divided by mass, such that P specific volume equals RT. This is our ideal gas law. It shouldn't be much of a ta-da because we knew where we were going, but it's nice to see it happen. Boyles and Charles were doing work in different ways on different ideas. They both came to a rule that said that if you have an ideal gas, my rule works. If you put those two rules together and play around with them, you end up with the ideal gas law. And the ideal gas law says that temperature, pressure, and volume, specific volume of an ideal gas, have a relationship, and PV on T or T on PV equals a constant. So let's go back. I'll make sure that that appears on the notes so that if my scribbling is a mess, we go up to P, we go up to A, blah, we go over to 2, there's the laws. I could have done that to B, and it would have made no difference to the analysis. That's the point. And so one of the reasons why I scribble all the things I've scribbled down is the next slide just says, if you substitute in, it's fixed. And a lot of people don't take the time to try to do it themselves. That ideal gas, that gas constant, that R is called the gas constant. The gas constant is specific for a particular gas, unless you apply Avogadro's law. So we've got the PV equals RT, we've got the P big V, P volume equals MRT. And then if we move on from there to Avogadro's, instead of mass, if we put in Avogadro's law, which is the relationship between mass and molecular weight, what you end up with is that P volume equals number of moles, universal gas constant, temperature. So if the R is just written as an R, it's the specific gas constant to the gas we're dealing with or analysing, so air, nitrogen, whatever. If we're dealing in moles and we've got the number of moles in there, then the R is RU, the universal gas constant, 8.314. The relationship between the universal gas constant and the specific gas constant is the molecular weight of the gas. Right, all this stuff connects and cancels out. So we've got enough minutes for you guys to actually calculate something. This is the bit where it's up to you whether you want to practice, right? I say that because if you've got the notes in front of you, you don't have to do anything. So it's up to you whether you want to try. I think it's worth having a crack, just to establish for yourself that if you mash the numbers into the calculator, you get the right answer, which is different to the thing on my page has the right answer. That's the point of practicing. So if the air gas constant is 287, calculate the density of air at standard temperature and pressure, STP. So what's standard temperature and pressure?
1 atmosphere.
Yeah, what's standard temperature? Room temperature. Normal temperature and pressure is room temperature and atmosphere. Standard temperature and pressure, 0 degrees. Okay? So, have a shot. We've learned one equation so far, so you don't have to guess which equation we're using. I'll give you 2.5 minutes. Yep. Try solving it in Celsius. Try it. What's going to happen in the equation? That's not deliberately smart-ass answer. The reason I say try it is that is the most healthy sense check you can ever use when you're trying to work out, should I do this in Celsius? You'll hear me rant about it a lot. If you try to solve the problem with a 0 and it explodes, the answer is probably no. Right, and that would be my major rant, is just forget Celsius exists. All right, I'll punch up to having stuff on screen so we can scribble through it. So if people wave around if you sort of got the answer or any of the answers on the page, if you tried it. Yeah, so there's some people twitching, not wanting to admit that they actually did the problem, but there was some, yes, we got it, yes, we got it. Okay, so we'll put this data in. I want to work out the density. Now the density is the inverse of specific volume. So it's PV equals RT. I don't have mass, I don't have volume, but I'm trying to work out specific volume, which is the same as trying to work out density. So density P on RT. So we put on our data. We've got 1 atmosphere over 287 times 0 degrees equals infinite density. Good. What did I do wrong? That's right, I used 1 atmosphere. So 101.3 over 287 times 0 equals infinity. That's better. What did I do wrong? What did I do wrong with the temperature? Kelvin, 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 Kelvin. Thermodynamics equals Kelvin. Please, 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 Kelvin. There are times where you will get away with using Celsius, but only by luck, only because you're doing a difference between 2 temperatures. If you purge yourself of the need to touch Celsius and only ever use it when someone gives you the initial information as Celsius or demands an answer in Celsius, if you do your maths in Kelvin, you won't go wrong, you won't get 0, which is good to know. And so this should have been 273. Now there's units, 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 units. The other thing that always goes horribly wrong in thermo questions is keeping track of your units. This guy sometimes gets given to you in joules per kilogram Kelvin, sometimes gets given to you in kilojoules per kilogram Kelvin. If I give it to you in joules, then I write my pressure in pascals. If I give it to you in kilojoules, then I write my pressure in kilopascals. Okay? That one is up to you guys. You get no hints, you get no tips, you don't get any reminders. Get it wrong, it's bad. I'll see immediately where you get it wrong because I will have worked out the answer 7 different ways to work out the most likely errors. Follow the units, never use Celsius. Okay? The easiest way to tell whether or not you're going to break the problem by